So, welcome to lecture series on advanced linear algebra. We have studied linear transformations, linear operators, linear functionals. We have also seen that if a linear transformations T is defined over a finite dimensional vector space, I mean if V be a finite dimensional vector space and W also finite dimensional vector space over a field capital F, then we have seen and T is defined, then collection of all linear transformations that is I have denoted LVW is also a vector space. And we have seen if the dimension of V is n and dimension of W is m, then dimension of LVW is mn. Apart from that, we have also seen that if I consider, say, let S denote set of all m cross n matrix over capital F, then there is a 1-1-1-2 map between the set of LVW and capital. There is a 1-to-1 map between these two sets. I mean, for each linear transformation in LVW, there exists one can associate a m cross n matrix over the same field place. Now, I will basically stick to, instead of linear transformation, linear operators. I mean, I will stick to this space LVV, set of all linear transformation from V into V. So, this is basically collection of all linear operator on V. For finite dimensional space, for a given order basis, one can have a matrix representations of the linear operator also. So, one can associate each linear operator by n cross n square matrix also. Now, we want to introduce an interesting phenomena for the linear operator. What is that? Eigenvalue of a linear operator, Let T be a linear operator on V, and V is a vector space over the field capital F. Let C belongs to be any scalar quantity belongs to the field capital F. C is said to be an eigenvalue of operator T, provided there exists non-zero vector alpha belongs to V such that T of alpha equal to C alpha. Here alpha is called as eigenvector of T associated to eigenvalue C, eigenvalue C please. So, this implies T alpha equal to C alpha implies T minus C times identity operator on V operating on alpha equal to 0. T is a linear operator on V and I is also linear operator on V. So, T minus Ci is also a linear operator on V. Now, T minus Ci operating on alpha equal to 0 for some non-zero alpha, this implies alpha belongs to V implies T minus Ci, this operator mapping non-zero vector to 0 vectors. So, this is singular operator. I mean the operator is singular. If V be a finite dimensional vector space, say dimension n, then T can be associated with the n cross n matrix. Then for a given order basis, T can be represented by an n cross n matrix, say capital A. So, if it is a finite dimensional, then we can associate this operator by n cross n square matrix if the dimension of this vector space V is n. And this matrix is also defined over the same field capital F. So, one can also define the concept of eigenvalue for a square matrix also. So, let me define concept of eigenvalue of a matrix space. So, let me define eigenvalue of a square matrix. Let A be an n cross n matrix over a field, say capital F. Any scalar C belongs to capital F is said to be an eigenvalue of A provided there exists a non-zero column vector, basically vector alpha, such that A of alpha equal to C alpha. So, this implies again A minus C I, this matrix, this is a n cross n matrix A and I is identity matrix n cross n identity matrix. So, A minus C I is again n cross n matrix. So, this when operating on alpha equal to 0. So, since there exists non-zero alpha such that A minus C I operating on alpha equal to 0. So, A minus C I is not invertible. So, this implies that determinant of A minus C I equal to 0. So, this gives determinant of A minus C I equal to 0 gives a polynomial equations in C, and degree of the polynomial, that is of the form I can say something like P C equal to 0, where P is a nth degree polynomial over the field F. So, I can say that when T is a linear operator on a finite dimensional space and C is an eigenvalue of the operator T, then T minus C I is singular. So, in that case I can say that determinant of T minus C I equal to 0. So, I can say that determinant of T minus C I equal to also 0 please. I mean when T is basically represented by some matrix A, then determinant of A minus C I equal to 0, which is equivalent to saying that determinant of T minus C I equal to 0 please. Here this P C is called as characteristic polynomial, and P C equal to 0 called as characteristic equation. Roots of the characteristic equation basically eigenvalues of T or A. So, if C is an eigenvalue, of T, then one determinant of T minus C I equal to 0, to T minus C I, this operator is not invertible. Please. Another important terminology is like this: let C be an eigenvalue of operator T. Let W be the collection of all alpha belongs to V such that the relation T alpha equal to C alpha is satisfied. Then this W is called as eigenspace of T associated to eigenvalue C please. So, we have defined what do you mean by eigenspace of an linear operator associated to an eigenvalue C. Claim W is a subspace of the vector space V. How? for alpha and beta belongs to W, we have T of alpha equal to C of alpha and T of beta equal to C of beta. Okay. T of alpha plus T of beta equal to C of alpha plus C of beta. So, T of alpha plus beta equal to C times alpha plus beta. So, is a linear transformation. So, this by using this property I can have T of alpha plus beta equal to this thing. So, this implies if alpha and beta with the in W, I mean if it is eigenvector associated to the eigenvalue C, then alpha plus beta is also eigenvector of T associated to the eigenvalue C. In fact, alpha plus beta belongs to W, please. Again, for any D belongs to capital F and alpha belongs to W, I have to show that D alpha is also belongs to W. Okay. We have T of D alpha is equal to D times T of alpha, which is equal to D times C alpha. So, this implies that T of D alpha equal to C times D of alpha. So, this implies D alpha also belongs to W. So, W is a subspace of the vector space P. Another interesting things, let A and B be any two similar matrices, matrices over the field capital F. Claim characteristic polynomial of A equal to characteristic polynomial of B. How? Okay, let PC denote characteristic polynomial of A. So, PC is equal to determinant of A minus C I. Given A is similar to B. So, there exists according to definition of similar matrices, there exists an n cross n invertible matrix P such that A equal to P inverse BP. So, this relations holds good. So, one can write down that PC, which is equal to determinant of A minus C I, can be written as determinant of P inverse B P minus C into I. One can write I equal to nothing, P inverse P. So, PC equal to, one can write down, this is now using the determinant properties, since P inverse is common in this side. So, I can say that P inverse this one into B minus C into I into again determinant of the P. And we know determinant of P inverse cancel out by determinant of P. So, this is equal to determinant of B minus C I. So, characteristics polynomial of B is equal to P C. So, both A and B have the same characteristic polynomials. This means what? This means both of them have same characteristic equations. So, means both of them have same characteristic values please. So, if A and B are two similar matrices, then the characteristic values of both will be same. Or in terms of the linear operator, one can also say similar way. Suppose T1 and T2 are two linear operator defined on a finite dimensional vector space V, where T1 and T2 both are similars. I mean there exists a linear operator say U such that T1 equal to U inverse T2 into U. So, in this case the characteristic polynomial of T1 and characteristic polynomial of T2 will be same. So, we have seen the definition of characteristic values of a linear operator or square matrix space. So, let us consider some examples. First, I will read the one small questions that is it necessary that every linear operator will have eigenvalue? Let us see through these examples. Let T be a linear operator, L dot O means linear operator on finite dimensional space R2, such that the matrix representation of T with respect to standard order basis V is say capital A, which is, let me consider this is like this 0, minus 1, 1 and 0. Now, question is, let us see whether this operator has eigenvalue over the real line or not. We have determinant of A minus C I, suppose C is the eigenvalue of the A, that is equal to I am getting as determinant of minus C minus 1, 1 minus C, because A minus C times identity matrix 1 0 0 1, when you subtract simplify it, then it is basically determinant of minus C minus 1 1 minus C, which is equal to I am getting C square plus 1. So, C square plus 1 is not factorizable over real numbers. That is C square plus 1 equal to 0. If you consider this characteristic equation, we have C equal to plus minus I is the only solutions. So, A does not have eigenvalue over real line, but it has eigenvalue over complex, but it has eigenvalue over complex number C. Let me take another examples. Say let me consider A equal to something So, if I consider this matrix A equal to 3 1 minus 1 2 2 minus 1 and 2 2 0, then we have determinant of A minus C I, we can easily calculate what is the determinant of A minus C I, and that you can check this is equal to C minus 1 into C minus 2 a whole square. So, characteristics equation, that is C minus 1 into C minus 2 a whole square equal to 0. So, C equal to 1 2 2 are the eigenvalues of the matrix A. So, A has eigenvalues 1 2 and 2. Okay. To say that one is an eigenvalue of the matrix A means I have to show that there exists a non-zero vector alpha such that A alpha equal to 1 into alpha. Similarly, to prove that to claim that 2 is an eigenvalue of the matrix A means I have to show there exists some non-zero vector beta such that A beta equal to 2 beta. Okay. So, for this now question is how to find the eigenvector associated to given eigenvalue C, please. So, eigenvector associated to eigenvalue 1. So, let me show how to calculate this one, please. Okay. So, we have say let alpha equal to x 1, x 2, x 3 transpose. So, that A minus I into alpha equal to 0 is satisfied. Now, so this implies I will have okay. So, I have to solve this system basically. So, this means that I have to solve basically what 2 1 minus 1 2 1 minus 1 and 2 2 minus 1 into x 1 x 2 x 3 equal to 0 0 0. So, I have to solve basically this system, please. If you see the A minus I, this matrix which is basically giving as this 2 1 minus 1 2 1 minus 1 2 2 minus 1, certainly determinant of this A minus I is equal to 0. I mean the rank of this matrix will be certainly less than 3. We can immediately see that 2 rows are same. So, and you can quickly check that this is having rank is equal to basically 2. So, rank equal to 2 means this system has solution space having dimension is 1, because rank plus nullity equal to dimension of the space, here dimension of space equal to 3. So, rank is equal to, you can quickly check this matrix equal to 2. So, nullity will be 3 minus 2 equal to 1. So, let us calculate that solution space please. So, this means that I have to solve 2 x 1 plus x 2 minus x 3 equal to 0, and other one is 2 x 1 plus 2 x 2 and minus x 3 equal to 0. So, if I solve it, I will have basically x 1, I mean 2 x 1 equal to x 3 minus x 2 and x 2 equal to 0. So, I will have x 1 equal to x 3 by 2, because if I subtract this these two equation I am getting x 2 equal to 0. So, x 1 equal to x 3 by 2. So, put x 3 equal to 1, I will have v 1 equal to 1 by 2 0 and 1 transpose as solution of a minus I alpha equal to 0. So, v 1 is eigenvector associated to eigenvalue c equal to 1. Similarly, we can find out the eigenvector associated to eigenvalue c equal to 2. If I do in the same way, okay, similarly we can find out the eigenvector associated to the eigenvalue c equal to 2 as v 2 equal to 1 1 2 transpose. So, we see that how the v 1 equal to 1 by 2 0 1 transpose, or we can multiply 2 when scalar quantity 2, then it is basically 1 0 2 transpose is the eigenvector associated to the eigenvalue 1 for the given matrix A please. Exactly same way one can also find out the eigenvector associated to eigenvalue c equal to 2, and that is as v 2 is equal to 1 1 2 transpose please. Note that this v 1 and v 2 are linearly independent. I mean to say, if the eigenvalues of the matrix A are distinct, then this corresponding eigenvectors are also linearly independent. You can consider it as a homework and check yourself please. We will continue more about this eigenvalue eigenvectors in the next class please. Thank you.